Hello, I am Ben Iglesias. Maciej and I decided to write our final paper on thorium-based nuclear power. I didn't know much about thorium before Maciej introduced the topic, but once I started looking into it, I was amazed at what thorium is and the potential it has if it were to be used in large-scale energy production. Thorium is element number 90 on the periodic chart of the elements. The isotope of interest is 232. Being 6 atomic mass units less massive than uranium-238 gives thorium some advantages as a nuclear fuel. In this presentation, I'll talk about some of thorium's advantages over uranium, including why it being 6 mass units lesser than uranium is a big plus. Advantages of thorium are in its worldwide abundance, its mineral and isotopic processing, lower construction costs for a new thorium reactor plant, fuel efficiency and electric plant efficiency, improved operational safety, production of fewer waste products than uranium fuels, as well as faster decay of the waste it does produce, non-proliferation benefits, adaptability to current reactor designs, as well as production of medical radioisotopes. First, abundance. Thorium is 3 to 4 times more abundant on Earth than uranium. Although India has the largest chunk of thorium of any nation on Earth at 16% of total reserves, here in the US we have 1.8 million tons of it in the Lemhi Pass between Montana and Idaho. That's enough to power our nation's energy needs for 3,600 years. Although thorium is found as a consequence of rare earth mining, it is actually most common in monazite in river and beach sands worldwide. Mineral and isotopic processing. Almost 100% of naturally occurring thorium is usable as a nuclear fuel. Compare this to about 0.72% naturally occurring uranium-235, and you realize that thorium doesn't need to go through an extensive and expensive enrichment process to get usable fuel. Thorium is usually found with other minerals that have varying specific gravities, magnetic, and electrical properties. Because of this, thorium is relatively easy to separate from the other minerals by using high-tension separators to remove electrically conductive minerals and by magnetically separating the rest. What's left is heavy monazite that undergoes a hot acidic bath to separate the thorium further. The entire process from mining an open pit to processing is much more simple and less extensive than mining and enriching uranium. Further, because thorium doesn't need to be mined deep underground, there is no radon concern for workers. Lower construction costs. A typical uranium-fueled reactor plant requires high-pressure rated vessels and piping, and a structurally sound containment dome to hold up to 60 pounds of pressure in the event of a loss of coolant accident. It also requires redundant safety systems to protect the health and safety of the public in the event of an accident. These items are very expensive and increase the cost of designing and building a pressurized water reactor plant. In the case of a liquid fluoride thorium reactor, these considerations are not required because system operating pressures are at atmospheric or low pressure. The fuel inherently also has a large amount of negative reactivity, and this allows for passive safety, allowing operators to walk away from the plant if an accident occurs without compromising public health and safety. Further, because thorium fuels are much more efficient than uranium fuels, construction costs are lowered because a smaller thorium reactor can be built for a similar output uranium reactor. A smaller geographical footprint is also required, which also affects the cost of a new reactor plant. Fuel efficiency and electric plant efficiency is enhanced by the following. Nearly all thorium fuel is burned and used in a thorium reactor as compared to 0.5% of uranium fuel. And also, fewer non-fissile isotopes are created that do not support the nuclear chain reaction in a thorium fuel cycle. Another fact that enhances thorium fuel efficiency is that estimates of energy density put thorium as having as little as 90 times more energy than uranium, while other estimates put this value up as high as 200. Thorium fuels are also 29% more thermally conductive than uranium, making it easier for heat to flow away. The thorium reactor can also take advantage of the Brayton energy cycle, which operates at about 50% efficiency. This is a very good improvement over the 30 to 33% efficiency we get out of a steam plant. Another thing that lends to the efficiency of a liquid thorium-fueled reactor is that xenon and other poisons are continuously removed, allowing even for a better load response on the powered grid if needed. Improved safety features. In liquid fuel designs, low operating pressures do not challenge containment structures in the event of a leak. As mentioned earlier, negative fuel reactivity allows for passive safety systems that allow operators to walk away or do nothing during an accident. In the event of a leak or loss of auxiliary power, liquid fuels drain to a drain collection system underneath the containment building, where outside of the reactor vessel, all fissions stop and the fuel shuts down. In solid fuel designs, thorium fuels have a higher melting temperature than uranium by about 500 degrees Celsius, adding an improved safety margin. Thorium dioxide is more chemically stable than uranium dioxide, and because of this, the fuel will not react with metal cladding. Also, the fewer gaseous isotopes produced will not add as much internal pressure stress to cladding material as uranium dioxide will. Radioactive waste products and faster decay of the products that are produced. Remember the 6 atomic mass units that thorium is lesser than uranium-238 by? Because of this, fewer transuranic elements are produced, since it takes more neutron captures and beta decays for thorium to form into a minor actinide. The minor actinides are the elements of major radiotoxicity concern when discussing long-term storage of nuclear waste. An operating thorium reactor will produce anywhere between 8 and 114 times fewer minor actinides than an operating uranium reactor. A thorium reactor does not produce any minor actinides while shut down, yet a shutdown uranium reactor will continue to produce them. Because of this, after 10 years of storage, 83% of thorium waste is stable, while at the same time about 1,600 times less radiotoxic than uranium waste. The remaining 17% of thorium waste products will need a 300-year storage requirement, while uranium waste will require hundreds of thousands of years to become stable. Proliferation. Thorium fuels produce about 3,000 times less plutonium than uranium fuels. The plutonium that it does produce, plutonium-238, produces so much decay heat that it melts and damages bomb-making materials. Further, while accompanied by uranium-232, ordnance electronics are damaged by the high gamma emitter, thallium-208, which is formed by decay of uranium-232. A significant amount of shielding and robotics would be required to even try to separate the bomb-damaging plutonium. Another interesting fact about thorium reactors is that they can be used to incinerate civilian and weapons-grade plutonium. As much as 1,000 kilograms of plutonium can be incinerated in a thorium reactor per gigawatt year. Adaptability with current reactor designs. Studies made worldwide have shown that the most commonly used reactors in America, the pressurized water reactors and boiling water reactors, can be modified for the thorium fuel cycle. The can-do reactors can also benefit from this, as it is also a commonly used reactor design in other parts of the world. This adaptability also extends to very high temperature reactors and molten salt reactors as well. Supply of medical isotopes. Thorium-229 is extremely rare, and it has a medical significance because it decays to bismuth-213. Bismuth-213 has been shown to be an effective alpha emitter that both fights leukemia and is very effective at killing HIV-infected cells. Other radioisotopes that can be created and separated from the thorium fuel cycle are actinium-225, astatine-211, lead-212, and radium-223 for a variety of medical purposes. Well, that covers the advantages that I have found so far that thorium has over uranium. I hope you found this presentation to be informative. Thank you.